Okay, now that we have a different scoring metric, I want to try to tweak these again. Okay, and sometimes it can be nice to hold one and change the others. Okay, so now we've got this 2.133. Okay, so what if I drop the number of samples down to 0.5? Will I get a difference? Well, let's run it and find out. Okay, and I'm going to try that just a little bit with each of these. Did I say 2 points? It's nice to write it down. Okay, so it was slightly worse. What if we go higher, like 0.9? Okay, and recall what this is each time you're making a decision tree, instead of using all the rows, you're using select. Okay, so maybe we did have the sweet spot at the kind of the 0.8. It's kind of not making a difference. Now, this min samples leaf we have not done much with. What if we just lower it? Okay, meaning, hey, we'll let it go further. Maybe you have some outliers that we're not letting it split enough times. And so, nope. What if we go higher? Okay, forcing more generality. Okay, and recall what we're doing here is we're making changes and looking to see, can I lower the score? I think that was not better. So maybe again, we're kind of close to a sweet spot around the 5. You could try more. Now the max features number of columns. I don't know. I'm kind of curious more about this one. Let's try 0.5. So what is this doing? Nope. Each time you build a tree, it says, hey, you know what? We're going to try to find the right split, not by looking at all the columns, but just by a percentage of columns. And so that's sort of interesting to vary. Wow, I feel like we really did land on sort of the sweet spots. Okay, what about this max depth? What if we go much higher? Okay, let's try a 12 here. Okay, and so what that means is we're allowing the data to find more splits. Now, if it's hardly making a difference, you're better off lower. Interesting, right? This is the... Surprised this one is so tough. That was definitely worse. Okay, we had the 8. What about 10? Not sure that we've tried 10. You can see at the time here, you could loop through all the options, but that's going to take time. And so in max depth, like with an estimator, sort of like the lower, the faster it's going to build. Okay, so maybe higher is better here. What if we try 15? And so max depth is sort of working in conjunction also with min samples leaf. And so min samples leaf is saying, hey, we're only going to let you go so far. Okay, meaning your tree can only be so convoluted, because if at the bottom we get to 6 different leaves, I changed it to 6, then we're going to say stop. But it is really hard to get less than 2.13. Certainly upping in estimators might do it. Okay. So we can try that. Now this will take certainly longer. I can also tell you that based on my own experience, using about 5 parameters to tune is often good enough. Okay, it's not actually the case that, the more you kind of deal with, the better off you will be. In this particular case, something else to consider could be going back to the data and actually looking at whether or not certain outliers could be removed. And so this data set, could require more analysis. I am not able to get under 2.13. Okay. We will be learning different models kind of in the future to sort of deal with this. Let me just highlight the code of what we have here so that you understand it. Okay. First of all, we're using cross-validation. Why? So that we don't have to keep changing the train test split and getting different scores, which is what we did earlier. Okay, that's number one. You've got to import it. Now, to use it, you want to define your model first. When you define the model here, nothing's been built. It's just setting model equal to, hey, it's a random forest. It's regression because this data set's regression. If you have classification, you want to use the classifier. And then what we are doing is adjusting these parameters to the initial model so that when it builds, we get different results. We're trying to tune it here, okay? And what have we been trying to tune? Max depth, which is the number of branches of the tree. Okay, it's how many questions you ask in the game of 20 questions for each decision tree in the random forest. The number of estimators is the number of decision trees. Okay, so Yeah, we haven't tried a small amount, which is sort of interesting. Um, like it's sort of like more is sometimes generally better is often how it works. Um, Not always the case though. Okay. But the whole structure of the random forest is such that you are in fact creating a bunch of decision trees. That's the in estimators, and you're sort of varying those trees with some random parameters so that you can obtain different results among the trees. Because remember, if it's the same result, it's just one decision tree. Okay. And technically, you could do it as a random forest if you set it equal to 1. Okay, that's one decision tree. You can see it is not better. Okay. Okay. Next, we looked at max features. This is like the number of columns considering when making a split. So why is this interesting? Because when you look at your data set, say, look here, and it's saying, okay, how do we decide where we're going to split the data? And it could say, well, you know what? If we ignore like the last 4 columns, only look at these, that's going to give different variation. And the next one might ignore those and look at these. And so it allows for more variation because it forces sort of the trees to take pathways through different columns. Okay. So this is saying, let's select 80% of them. I can't remember how low we went. I mean, you could have like, if you can have 200 trees, I mean, you could have like a low value here, right? You could try that. Okay. Okay, next. Oh, sorry, I meant to change it here. Remember, that's that other score, that R2 score. I haven't tried it as low as 0.3. Okay, so next up, I'm going to talk about max samples because that's similar to max features. Just like max features only looks at a certain number of rows to kind of build out your tree per split. Oh, sorry. I'm sorry. I paused deeply because this is not the one with the scoring metric. I was like, did we do that much better? I was a little skeptical. The negative mean squared error here is this one. You can see it looks like it's not doing better because we have an R2 score, but it's a different scoring metric. Okay. So what max samples, it says is that, okay, we're going to modify the number of rows each time. Okay. Each decision tree, instead of using the model, let's just use like a different percentage. Okay. You could try some different numbers in combination. And finally, we have, as far as these parameters go, min samples leaf. This is saying, you know what? We're not going to let the decision tree get too far down. We're going to say, once you get, you're going down and asking these questions. Once you only have 3 rows left, if I change it to 3, stop. Okay, you have to stop right there. You cannot continue to do any splits. So that's giving it a lot of latitude. I kind of just want to try higher and lower on some of these to see what we get. Hardly making a difference. Like, what if we forced it to be something high and then that's going to counter the max depth a lot, okay? Yeah, it's too much. Okay, and so I think we had 5. Okay, so those are the parameters that we're changing with the random forest, okay? But they're changed here, okay? This is where it all happens. That's a better score. Cross-validation, you can see we're close to cracking the 2.13. Cross-validation is think of it like a machine learning model, okay? So what does it do, okay? What it does, it takes a model as input, which we've been redefining by making some changes. It takes an X and a Y. Okay, it's got to have data. Okay, you put it in there. Now, this CV is the number of splits. I've been doing 5 splits. Okay, we looked at 10. I think this one has 10, and it wasn't really making that much of a difference. And keep in mind, it's not really about adjusting CV to get like a better score. What you're doing is you're using CV to get a score that's more reflective of reality, right? So if you change this to 6 and you get a slightly better mean, that's not really the point. The point is set a CV and then within that, make your changes to see if you can improve the score. Because when it's all said and done, it's not about cross-validation. It's about this. It's about the model that you end up with and that you are going to use to make predictions. okay? Additionally, we've got the scoring here. We've looked at two scoring metrics, the R2 score, which we've sort of defined as the percentage of data that's accounted for by the model, okay, compared with the negative mean squared error metric, which directly gives us the root mean squared error. Okay, this is the norm in regression, and it clearly means, as stated here, we did not improve. The RMSE is the error that you get, okay, when you're trying to make predictions. All right. So what 2.13 means is that, you know what, when we look at all of the folds in our test data set, okay, and we compare how many rings it actually has versus what the model predicts, on average, they're off by 2.13. Okay. You can compare them directly to see what you get, right? We've done stuff like this before. So if we looked at like the first, let's look at the last 5 rows, right? Okay, there's the last 5 rows. It shows the number of rings. What does the model predict? Okay, this is a little interesting. Why? Because this model here has not been fit on the data, actually. And so you can't directly use it to make predictions, okay? This model here has been used with cross-validation to get scores. And that's sort of the point of emphasis here. We're kind of working with the model to improve the scores. But if you want to make a prediction, okay, what you could do, and this, let me just show you. You could put this model in here, and in effect, you could just train it on all the data. Like maybe you're done and you say, you know what, I'm finished. This is the best model I can get. I'm going to train it on all of X and Y now. Okay, this is what you do at the very end of machine learning. We're just doing an example here. But the point is that you can then predict the last 5 rows. Okay, what does the model actually predict for those last 5 rows? Now, this particular case, it's trained on the data. So in effect, it is like curve fitting. So really, you know, maybe we should do it on the train. You know, we already split the data. And then we'll take the test tail and we'll compare that to the Y tail of the test. Okay, so here we go. That's our model. There are the predictions, and we can compare that to Y test dot tail. Fail. Okay, and you can see it gives 10, 10, 9, 10, and 11. Not bad, right? I mean, when it's 9.4 and the prediction is 9, really strong, right? And even the 11 to 9.9, that's only off by about 1. Okay, you can see this first one is kind of off the most. So it's kind of fun, and like, you know, you could just even get like more info sort of on how the model is doing. Okay, what if I look at the first 5 rows? What kind of predictions do I get? And you can see there they are. You get more variety. Well, what's the head of the test set? Okay, let's find out. Look at this. This is interesting. So 13 to 13 is spot on. It's off by just 0.2. This one is off, okay? This is where you get some rough roads. Like some of the high values might be causing some of the problems, so you can start to learn things sort of about it. 8 to 10, not bad. 8.85 to 9, phenomenal. 10 to 11. So it looks like it's doing pretty well with some of the middle data. Okay, so there's some more insight to it. Hopefully you enjoy working with the random forest. The next series of lectures, I will introduce my favorite of all the sklearn models.